Hello, my name is Derian Morphew. This is my final journal club presentation over deep learning. For the paper that I chose, it was titled Martensite Star Temperature Prediction Through a Deep Learning Strategy Using Both Microstructure Images and Composition Data, published in the Journal of Materials by Dr. Yang out of the Beijing Institute of Aeronautical Materials. The reason I chose this, my last two journal club presentations have been related to elastocaloric effect materials, which are materials that I do research in as well. Um, but I guess not so surprisingly, there weren't any papers that I could find that used deep learning specifically as a strategy in any type of elastocaloric effect research. And to a degree, that makes sense. When I think of deep learning, I often think of image processing or audio processing. And so most of the elastocaloric effect machine learning space in literature is regression type models like Bayesian or Bayes theory. And so there was not a lot of research over elastocaloric effect materials with deep learning. So I came across this paper, which is it's a very simple and short paper, but very useful over predicting Martensite star temperatures based off of SEM microstructure data as well as composition. Um, and so what they did was they heat treated and processed four different steels. And so there's 24 total samples because for each type of steel, they varied the annealing temperature six different ways. And so that gave them a total of 24 different samples. But for the four different steels, they varied, as you can see here, they varied the manganese composition. And in the paper, they stated they try to keep silicon and carbon relatively similar across all four different steels because they wanted to mainly just vary the manganese. And so this is the heat treating process. You can see here where um, here, when I get to this last annealing step, they each steel was annealed at a different temperature based on its manganese composition percentage, and then they annealed it for six different times, basically for all four steels. And so this is just a picture on the right, an example where I think this was steel A, steel B, steel C, and steel D here. Um, and so they had SEM images as their microstructure images. And so this is their result of plotting Martensite start temperatures for each of those 24 samples. And they found the Martensite start temperatures by thermal expansion temperature curves from dilatometry experiments. This is pretty standard. Another way to think about it is just maybe solid liquid transitions and DSE experiments is a way to find the starting transition temperature between phases. It's similar for thermal expansion, where they're looking for a nonlinear change in the thermal expansion temperature curve, where they identify the Martensite start temperature. And so this is the result. So they had 24 data points basically to work with, which is not a lot for deep learning. And so I will get to how they data augmented in a second, but they used the convolutional neural network for their prediction with the structure of the neural network seen on the right, where they used five convolutional layers and five max pooling layers. Um, and so what kind of separated this paper from a lot of the other papers that I found throughout the literature, um, especially for predicting Martensite start temperatures in steel specifically, is they correlated composition data and microstructure images. And they did that here. As you can see, they basically just multiplied the composition of carbon by basically each of the pixel values in the pixel matrix, the pixel value matrix. And so this is the neat thing about deep learning is, or machine learning in general, if you don't already know, but basically there's no physical meaning of just multiplying the composition with the pixel values of the image. But what it does is for machine learning, it allows you to tie composition directly into microstructure, which was the goal of this paper, because the authors had stated at the beginning in their motivation that it's well known that Martensite start temperature depends on both the composition of your steel, as well as the resulting microstructure from various types of processing and heat treating. And so how they accounted for both was just multiplying the compositions for each of the three channels, their carbon, manganese, and silicone compositions by each of the uh, pixel values in the matrices for these images. And so then for data augmentation, they cut their initial 1280 by 1280 pixel value matrices and basically cut them into sub matrices of size 224 by 224, which gave them more data sets to use, basically expanded their image pooling set. And then they also went through rotation and mirroring of the sub matrices to basically expand from their initial 24 data points to 20,475 data points, which is enough for their convolutional neural network. And so what they showed first was basically their loss function to find out how many epochs they needed, and they decided right around 200. If you're not aware of anything, if you underestimate the amount of epochs, you tend to get underfitting, and then if you overestimate, say you use a lot more after the loss function is kind of flattened off, this paper at least argued that you would risk overfitting, and so they decided that the loss function leveled out right around 200 epochs, which is what they used for the remaining data that I'll show. And so you can see in this figure here, they show their mean squared error as well as their mean average error and their R squared value. And for their roughly 20,000 data points. And from training to testing and validation, there's a little bit of an increase in the mean absolute error, which is indicative of a little bit of overfitting, but the author said, and I'll show in a little bit, that they weren't really worried about the overfitting, especially because the R squared value too is pretty similar for training, testing, validation. So they determined that overfitting was not an issue. But as you can see here, the predicted MS and training MS, predicted in testing, and predicted in validation MS temperatures, they align very well, especially with my next slide that I'll show. You'll understand how they align well with other types of CNNs and similar literature. So this is what I just showed, basically is composition and microstructure based convolutional neural network, which was aimed at making the prediction of MS better than other machine learning models that have been used for similar predictions, which is shown here. And this is a traditional CNN for MS prediction, which only uses microstructure. So the step that these authors took in multiplying the composition times the microstructure, traditional CNNs in this space don't do that. They just account for microstructure. And so you can see here, mean absolute error has a spike from training to testing and testing to validation, and the R squared value slowly starts to decrease. And so the authors have stated that this model seems to have overfit based on these parameters, but you can also see just from comparing the predictions to the actual values, it is much more widespread and varies a lot more from the prediction compared to your composition plus microstructure based CNN. The mean average error and R squared values are better in this case in this paper compared to traditional CNNs, which basically highlighted the main contribution of this paper. Like I said, it was a short paper, but I found it to be pretty useful and straight to the point, where this composition microstructure, being able to basically integrate the composition into the microstructure for the CNN led to more accurate prediction of MS values. And that's essential for tailoring properties of steels, especially during the design and processing step of annealing, knowing what temperature to anneal at, how long to anneal to get desired properties. And so I found this paper to be extremely insightful. And even though this was specifically for steels, it definitely can be applied to shape memory alloys for elastic materials, where MS temperature is fairly important as well. It's another parameter to consider. And so you have microstructure images and composition. This can easily be applied to shape memory alloys as well. So that is all. Thank you.